Good morning, students. In our last class, you must be remembering we have done up to the torque on a current loop placed in the uniform magnetic field. Torque on a current loop placed in the uniform magnetic field. Okay, today our discussion is in continuation with that. A very important discussion regarding a very important device, that is a moving coil galvanometer. We are today going to discuss regarding the moving coil galvanometer. Alright, with the help of the moving coil galvanometer, the current through a circuit can be measured. But before I start with this, I just want to tell you a few things. You know, in these days, CBSE has issued a syllabus. They have deleted some portion of the syllabus which was there always in air, that some portion will be deleted of our class 12 syllabus, and they have done it. In this chapter, in our present chapter, I will be sending that deleted portion in the WhatsApp group also. And moreover, when we are doing this magnetic effect of current, I just tell you, they have already deleted a long topic which we have already discussed, is cyclotron. Cyclotron is no more in our syllabus now. Please note it. The topic cyclotron has been completely deleted from our syllabus of this magnetic effect of current. Be careful about it. Okay? And other topics also I will send it to you in the WhatsApp. Okay. Now, let us come to the moving coil galvanometer, with the help of which the current in a circuit can be measured. In a moving coil galvanometer, what happens? First of all, as far as our moving coil galvanometer, the principle of moving coil galvanometer is concerned, it is based on the principle that when a current carrying coil is placed in a magnetic field, okay, when a current carrying coil is placed in a magnetic field, you can write, is placed in a magnetic field, then it experiences a torque, which we have already discussed. So when a current carrying coil is placed in a magnetic field, it experiences a torque, and that torque depends upon the magnitude of the current flowing through the coil. The torque depends upon the magnitude of the current flowing through the coil. This is the principle of the moving coil galvanometer. Now we are coming to important parts, the construction part of the moving coil galvanometer. It consists of, two pole pieces, N and S. These are concave shaped pole pieces. N and S are the concave shaped pole pieces. Alright, you know concave shaped. These are the two concave shaped pole pieces, and between these two pole pieces, here there is a coil, rectangular coil, within which there is a soft iron cylinder. Alright, here capital I is a soft iron cylinder. It's a soft iron cylinder. I is a soft iron cylinder, and over that is placed inside a non-magnetic aluminium frame, over which insulated copper wires are wound. On that non-magnetic frame, the insulated copper wires are wound, as shown in the figure. Insulated copper wires are wound. Alright, these copper wires which are wound, they have definitely the two ends. One end is internally connected to one end of the, here, see, hair springs. Here is a hairspring, here is also a hairspring, here is a hairspring. What is this hairspring? Hairspring is made up of the material. Hairspring is made up of the material. That material is known as phosphor bronze. Hairsprings are made up of the material known as the phosphor bronze. I just tell you, phosphor bronze is a very good elastic material. Very good elastic material. Moreover, it is non-magnetic, but it's a very good conductor of electricity also. These are the characteristics. I tell you characteristics of this phosphor bronze. Why it is used to make the hairspring? Because it's a very good elastic material, you can note down. Second, it is non-magnetic in nature. And third, it is a good conductor of electricity. And fourth, it is chemically non-reactive. That's why when the current will be flowing, heat will be produced, it won't be oxidized. These are some properties of phosphor bronze wire. What happens here? These two here coils, the ends of this coil are internally connected to one end of the phosphor bronze or the hairspring, and the other end goes to the external terminals T1 and T2 through which the current will be entering in the galvanometer. But where these hairsprings are there? Actually, hairsprings are there inside this. Here, see, this coil is kept here with the help of the two jeweled bearings. Look, these two are the two jeweled bearings which are giving it the support. Okay, the coil is pivoted. The coil is pivoted between these two jeweled bearings, and here the hairsprings are internally connected to the two ends of the coil, two ends of the wire's wound. Here, this is a scale on which an aluminium pointer can move. Due to the movement of the coil, the aluminium pointer will move. Alright, these are some important parts. All the important parts are shown and leveled. Alright, all the important parts have been shown and have been leveled. Now, these are some important parts. Clear? Now we are coming to the working part. After that, let us suppose these two terminals T1 and T2 are connected to an external circuit, so that the current will be entering through T1, circulating through this. Let us say it is circulated like this. Look, let us say this is the direction. The current is flowing anti-clockwise like this. It is coming, flowing through the whole coil, and again it is coming out from here continuously. Then what will happen? We have already seen, according to Fleming's left-hand rule, the magnetic field will be definitely from north to south. That means, according to Fleming's left-hand rule, from north to south in this direction magnetic field. Alright, current is in downward direction. So on the left side, left vertical end of it is moved towards us. That means the coil has the effect. The coil will have the rotational effect like this. Isn't it? And as the coil will rotate, the pointer will move on the scale. As the magnitude of the current will be more and more, okay, the torque will be more and more, and the pointer will be shifting more and more on it. Alright? This actually happens. Basically, this happens. As the current will be flowing, due to the Fleming's left-hand rule, the coil will be turned. And when the coil will be turned, as the coil will be turned or rotated, the pointer will also move on the scale, and it will show the reading, and from there we can calculate the current. How calculation of the current will be taking place, I am coming to that point later on. Alright, this happens. My dear students, for your convenience, when I will upload this video, I will send you the writing part, especially the construction and working part also with this, the notes. You can prepare the notes from there because it's a full length question. I'm just telling you. Alright, this happens. Now let us come to the theory part of it. That is theory part, that is definitely a mathematical part of it. So let us come to the theory or the mathematical part of it. Okay, mathematical part. What will happen? The coil will be turned, due to which the coil will get a, the coil will get a deflecting torque. There will be a torque. called deflecting torque. How much will be the deflecting torque? Tau D should be Ni here, I think Niab cos theta. I hope you are remembering my last class's last discussion, because what will happen? The coil will be turned. Coil will be turned means the plane of the coil will make an angle theta with the direction of the field. I write here. Here, you know, I think all of you can understand. N is the number of turns. A is the area of coil. I is the current flowing through the coil, and B is the magnitude of magnitude of the field. And what is theta? Theta is the angle between direction of field and plane of coil. Alright, direction of the field and plane of the coil. Here it is the deflecting torque. Look, this is regarding here the torques are acting. I will come into the next part in the next lecture.